starting that, let me discuss one of the famous modeling process that we normally encounter in machine learning techniques is the discriminative modeling. This is one of the I think most of you may be knowing it, but let me discuss it here so that the picture becomes clear that what is the difference between discriminative and generative modeling process in machine learning. So here you can see we have three different blocks. So the first block is the training data block, and this training data block actually consists of training set which we will be using for our machine learning task. And in this we have, let us say for example, cat images and we have dog images on the right side. So if we have these images, what we will do is we will actually, along with these images which we have over here, we append a label 0. That is, we are appending a label y equal to 0 with these cat images. And for the dog images, what we are doing is we are appending y is equal to 1 for these dog images. And all the images that you have here, that is cats and dogs, they are actually x. So basically, you have a training sample xi comma yi, and where I is actually running from 1 to capital N, and N is basically the number of training samples that you have in the data set, and xi are the images of either cat or dog, whereas yi are the labels which I have just discussed, that is 0 and 1. So 0 corresponds to cat images, 1 corresponds to dog images. So what discriminative model do is it actually tries to come up with a line fit or maybe a hyperplane in higher dimension, which actually distinguishes distinguishes cats from dogs. So that is one of the important tasks of discriminative model. That is, it tries to come up with a hyperplane here which actually distinguishes cats from dogs. So this may be, this is a image of a cat, let us say, and this is an image of a dog. So the important thing is how to come up with this line, a separating hyperplane in higher dimension, which can actually separate cats from dogs. So this line actually is created by this discriminative model. So once you have this discriminative model, ready, then you can make predictions out of this in terms of the probability. So for example, if the probability that comes out from this discriminative model is 0.83, that it might be, then it is like, you are 83% confident that whether your image is cat actually. And the rest of the probability, you are saying that it's a dog image. So basically prediction is always coming out from this discriminative model in terms of the probability value. So for example, 0.83 is one of such example. And here the test image that you will use has to be different from the training sample that you are using for discriminative models. So this has to be kept in mind that the images that you are using here are a different data set which is fed into the discriminative model for creating the hyperplane, and test images that you will be having are in separate bag and they cannot be in the training bag, and this test image will be fed into the discriminative model to get you the predictions. So 0.83 corresponds to the prediction that you get from the test image. So this is a general high overview of discriminative model, which I think most of you must be knowing it because this is actually the first encounter that you will see when you study machine learning tasks. So now the another important thing that we are now discussing is generative modeling, which is actually new and it's some way or the other related to what we will be discussing in generative adversarial networks. So these generative modeling, what happens is, again we have these three blocks. The first is a training data block, second one is the generative model block, and the third one is a generated sample block. So let us discuss each of these in detail separately. So in training data, in our case of, if you remember, in case of discriminative model, we had cat images and dog images. But in case of generative model, if you observe that in training data we have only cat images, there are no dog images. Why like that? Because here we are solving a problem of generation. We are trying to come up with generating new samples. So in order to generate new samples, it's important to learn from one class, like how we can do that. So here what we are doing, we are actually selecting multiple number of cats. These cats are we are taking a large corpus of these cat images, and then these cat images are actually the training data which we will be using for feeding it into the generative model. And this generative model, what it will do, it will try to actually come up with a probability distribution. So if you recall that what we started off with is, in generative model, so what we want is, if you recall, I'll just go back to this slide. So if you see, what we are trying to do is, we are actually trying to formulate a probabilistic density function. And once we have this, we can, sample from this to generate new data. So right now, what generative modeling is trying to do is to find out a probabilities model for this data set. So the important point is, let me discuss here. So here you have this training data. So this training data is actually fed into the generative model. And what is this doing is exactly is, let us say you have an image which is of size 28 cross 28. Let me draw it like this. So it's a 28 cross 28 image size, let us say. So what happens is, if you reshape it into a one-dimensional vector, then it becomes 784 cross 1. So it's a one-dimensional vector. So in higher dimensional space, let us say if I have a high dimensional space which is of 784, then each of you will agree that in this higher dimensional space, which is of dimension 784, each of these images, so for example, this particular image which I am saying, will be represented as a point here. So this 28 cross 28 will be a vector, and that vector can be represented in a higher dimensional space which is of 784 as a point. So if we collect all these images in the training data set and represent them as a point, then what will happen is, these, because they are cat images, so somewhere or the other, they will all cluster together into some space which is, they are all close somewhere in this higher dimensional space. But the important point is, we do not know that what contour it is having in this higher dimensional space, because I hope you know the contour thing. Like, if you have a probability distribution, so if you try to see the if you try to, this is a two-dimensional probability distribution. So if you try to see a projection of this on 2D plane, there will be a contour, right? It will look like this. For a Gaussian distribution, it will be a ellipse, which is a contour in two-dimensional. So somewhere or the other, I'm trying to give you a intuition on on this type of contour that will be formed in this higher dimensional space. And it's not necessary that the distribution that you have here in case of these cat images will be different. So right now, for easiness, I have displayed this as a Gaussian distribution, but it might be the case that this particular training data set will have some random probability distribution like this. So we do not know. So the important thing is, what we are trying to show here is, that the contour plot can be, anything, something like this. So I'm trying to, just simplify this matter by showing you that, suppose this particular training data set is, a Gaussian distributed, just for simplicity. So what we are trying to show here is the contour plot of that. But it is not right, because the distribution can be totally different. It can be a multimodal distribution, because we do not know on what distribution these cat images which are over here in the training data set lies. So for simplicity, I'm assuming it's a Gaussian one. So there will be an ellipse like this in a higher dimensional space. So now the important thing is, uh, what is the objective of this generative model? The objective of this generative model is to come up with this distribution, which is, let us say, D. That is the objective of this generative model, to estimate this D. So this D is the projection of a higher dimensional Gaussian distribution onto the plane. So this is so you can understand what I'm trying to say here. So this is actually a D which I am representing here. So this is the objective of generative model, to come up with the distribution that encompasses all the cat images which are inside this. Now what happens is, now you are trying to feed a random noise here. Let me show that. So this is basically a random noise which you are actually feeding into the generative model, and then what you will get as a generated sample. So what I am trying to show here is, now the noise which I am showing over here is actually somewhere like, some seed here, which is not exactly the actual training data set, but this is a random seed which I am taking. From this seed, if I try to, find out, the value of that, this value which we obtain like from this seed, let me draw like this. So this value that you obtain here, which is then converted, is giving you these images. So the important point that has to be noted here is that these images which you are getting over here are also cat images, but these cat images are not the same cat images which are here. So they are different. That's why this generative modeling name comes up, because you are trying to generate new images or new cat images which are completely different from the existing images which you have over here on the left side, which is the training data set. So this is basically the concept of generative modeling. So what we are in mathematically, what we are trying to say is that is when you discuss the discriminative model, which we have discussed earlier, it estimates the probability of y given x. That is the label which we are trying to predict in discriminative model given the observation x. This is the basic fundamental of discriminative modeling. Whereas the generative modeling estimates P of x, which I was telling you earlier here. So it actually estimates this probability first, which is actually I am writing it as D. So the probability of observation x. So if the data set is labeled, so this is something not required. But the important thing is what I was telling, that you are estimating the probability distribution, and from this probability distribution you are generating new data set. That is the basic fundamental of generative modeling. Okay, so once generative modeling is finished, now the second term that comes up is adversarial. So if you recall that GANs are actually generative adversarial networks. So the second important thing is adversarial, which is another important term. So if you look into the dictionary, then adversarial is something like, there is a conflict or an opposition that is going on somewhere, in nature. So in generative adversarial network, we will try to see what kind of adversary or what kind of opposition is happening. But to make this picture clear, I have a snapshot here for for this adversary that is going on in this particular picture. If you see, then what is happening here is that we have this cheetah actually, which is trying to chase deer, because obviously cheetah wants to eat deer, so that's why it's running behind. It's running just to catch deer. So the important thing here is what kind of adversary is happening over here. So the adversary or the conflict or an opposition that is happening over here is in terms of the distance. So if you see the distance between the two, let us call this as D. So what is happening is the adversary or a opposition is happening in terms of D. So how this opposition is happening? The opposition is happening in the sense that cheetah wants to actually minimize this D. So cheetah actually wants to minimize the distance between the two, because obviously he wants to eat the deer, so that's why it's trying to minimize the distance. Whereas deer wants to escape cheetah, so what a deer wants to do is to maximize the distance. So somewhere or the other, there is a game which is going on over here, which is where minimization of the distance is happening with respect to cheetah, because I'm representing cheetah by C. So there is a minimization of the distance which is happening with respect to C, and with respect to deer, what maybe these numbers, these variables are same. So maybe let us keep it as capital D only. So this D is basically the deer. So you are trying to maximize the distance with respect to deer. So there is something like a game theory type of thing going on over here, where you have a opposition between, like, one component is trying to decrease it, other one is trying to increase it. So there is a max min type of optimization strategy going on in nature, as you can see here. So similar type of behavior we will see when we will discuss generative adversarial networks. Then we will derive the laws for that. So there you will see there is something like max and min coming up over there also. So you just keep this in mind, that this max and min is coming because of the adversary or a conflict or an opposition which is happening in generative adversarial network. So that's what we have here. So this is adversary concept. So now, as we have discussed each of these three terms, generative, adversarial, and network. So I hope you must be, there is no doubt in this of understanding. Like if you have any doubts, you can ask me. But as far as the terms concerning the generative adversarial network is concerned, I think picture will become clear more. But for time being, I think if you have any doubts, let me know. Uh, yes.
Sir, sorry to interrupt.
Yeah. Yeah.
Can
Please.
you please switch on your video?
Oh my God. So video is, oh, for my video.
Yeah,
Okay, okay. I thought that,
yeah.
just a second.
Actually, I was right.
Yeah, okay. Yeah, please.
Yeah. So now you are visible.
So do I have to open it for all time?
Yes, sir. Fine.
Is it required? Just asking.
Yes, sir.
Okay.
It's
Okay.
good because we are recording the session, no?
Okay, okay, fine,
So
fine.
it will be good.
Okay. So here we have this thing here. So I think these terms related to generative adversarial network, I hope it's clear to all of you. So let us move forward. So here, what I'm trying to show is like, the progress that is made in case of the phase generation, which is happening in generative adversarial networks. So here, if you observe, it's a research which is happening. So it started in 2014, this generative adversarial network. It started in 2014 and it's continuously going on now also. So people are trying to improve it, but this slide is showing you for the time span of 2014 to 2018. So here you can see that in 2014 when the paper came out by Ian Goodfellow, who actually proposed this work, so the type of images that you were getting here was something like this. So obviously this is a huge success at that time, but the quality of the images that you are observing are not that good. But as the time progressed from 2014 to 15 to 16 to 17 to 18, you can see how the size of the images are increasing as well as the quality of the content of the images is increasing. So this shows you like the progress that is made in the research community from 2014 to 2018. So later on, like when you will see nowadays, people have still advanced more than this. You can find tons of literature on GAN. So there are like thousands and thousands of papers which are published every day. You can see it on Google Scholar. Just type generative adversarial network, you will come to know how many people have cited this particular paper, particularly for Ian Goodfellow. So it's a landmark paper, and it sets up a different stage in terms of a new area where people have explored their research and avenues. So this was just a brief history of this. So now we will come back to the GANs and we will try to understand the basics of this GAN. We will try to understand how what is the mathematics behind it. We will try to derive the loss functions for this GAN from scratch. So everything will be from scratch and we will not assume anything. So you will see a lot of mathematics going on in the coming slides. But to start the discussion, so this is just a brief summary of what we had discussed in our earlier slides. So the brief summary, what it says is, GANs are basically neural networks that are trained in an adversarial manner to generate data mimicking of some distribution. This is just what I have discussed right now, that we are trying to come up with the distribution and we are using some adversary type of activity. And GANs are nothing but they are two neural networks which actually are trained in an adversarial manner to fight with each other in adversarial situation and tries to mimic some distribution. So this is a very high level explanation of GAN. So the two classes of model which we had discussed in just a few slides back was discriminative model, which we just discussed, and then we had a generative model. So a generative model is what? So let me describe these lines. They are very difficult to understand, but it will become clear once I will discuss the this statements in some sort in pictorial representation. So what it says is a generative model G to be trained on training data X. So you are trying to find out a model G on the training data X. After sampling from some distribution true, distribution D is the one which gives some standard random distribution Z, produces a distribution D hat which is close to D according to some closeness metric. So I know it's very difficult to read these lines because they are all interrelated and it's difficult to understand. So let me try to explain it in terms of the figure, that what these generative models are trying to do. So and then we will come back to these lines again. So this is basically a very rough sketch of, a 1000 feet overview of what generative adversarial networks are trying to do. So let us say we have a true distribution, which we have already discussed, that we are calling these distributions as D. So if you see here, we have a capital D. So we are trying to find out this true distribution, which is encompassing the training samples which are there inside it. So you can see all the dots which are there inside are basically the cat images. You can take this as your reference. So these are the original cat images, and D, the capital D, is the distribution which we are trying to find out. And inside these cat images, each of these cat images, we are representing it by capital X, which is actually a random variable sampled from this distribution capital D. So this is what we are actually representing mathematically. Now what we want to do is we want to estimate this distribution which is capital D. So there are two ways of doing this uh, estimate. The first way is this generative adversarial network, which I am trying to explain here, but I will show you what is the second way. So the first way is this. So our target is to calculate this distribution capital D. So for that, what we do is we create a neural network, which we are calling it as a generator. So this is a box, a black box, where we have this neural network inside. So you can put neural network or you can put convolutional neural network in here. There is no problem. And if you recall the generative GANs, the generative adversarial network, this network is the network which I was telling you is this network. So the term network is coming because you are using neural network or CNN here in this block. So what this block is doing is it is actually somewhere or the other taking a random noise, which is Z, which you are sampling from a distribution capital Z. And this capital Z, though I have drawn it arbitrary shape, but normally what they do is they take normal distribution or Gaussian distribution. So somewhere or the other, this diagram is which I have drawn, like this, should not be like this. It has to be, ellipse. So you are taking a random noise from this ellipse. So it's a contour plot actually for this Gaussian or normal distribution. So what we are doing, we are actually taking a random seed, a random noise from this distribution, and then what we do is we feed it into this block, which is capital G, and what happens is this G actually transforms this random variable, which is Z over here, or a seed you can say, into G of Z. So you can say that this is a random variable which you are actually randomly sampling from this distribution. So when you pass it through a transfer function capital G, then the random variable becomes transformed into G of Z. So this is what we have here. So all the data points which are lying inside this is G of Z. And this G of Z obviously will have some distribution D hat, which is like this. So it will also have some distribution D hat. So our target is to actually make this D hat as close as possible to D. That is our target. And the closeness of these two distributions, which is D and D dash, can be done in two ways. The first way is to use KL divergence, which is one of the concepts where you try to find out how the two distributions are close to each other or not. So that is done through KL divergence. Another one is Jensen-Shannon divergence. So these two divergences are basically used for calculating the closeness between the two distributions, which are D and D dash. So this is one way of doing it. Another way of doing it is using a model, a machine learning model. So we will see how a machine learning model will help us in calculating the closeness of D dash and D. We will see in the coming slides. But the important thing is this KL divergence and Jensen-Shannon divergence, if you go to the theory of that, you will observe that they are actually, they work very well for small dimension vectors like 2 or 3 dimension vectors. But for higher dimension vectors, the KL divergence and Jensen-Shannon divergence does not work properly. So in order to avoid instability issues of KL divergence and Jensen-Shannon divergence for higher dimensions, we use machine learning models that can help us in in making these closeness metrics, in order to judge that how close this D hat is to D. So what is our target? Our target here is like how to make this D hat as close as to D. So if we can make this D hat as close as to D, then this generator is completely trained. What we can say is this generator is completely trained, and it can now generate samples which are similar to the samples which you have over here. So the important thing is how to train this generator network, how to train the weights of these generator network so that this D hat becomes as close as possible to D, and then we can have a generation of new samples. So this is the concept of generative adversarial networks. So now we will see how we can do that. So if you observe here, this is just showing you again advanced version of what we have shown over here. And what it is as you can recall, this is actually the original data set D, and all the images which are there in this D are basically the images which are the cat images, the original cat images of the training data set, and they are actually sampled from this capital D. This is what I have just explained you. Now this is the generator. It takes random value or a random seed from normal distribution, and it feeds into this generator block. And what happens now is, in the first 10, or maybe this I have given you just a brief snapshots of the iteration, but it can be different. So what we are trying to do is we are trying to run it for, let us say, 10 iterations. So in 10 iterations, what will happen is it will come out with this, let us say, this type of boundary, and you can see that this boundary is not same as this boundary. So whatever samples that you will get from this particular distribution will not be the same as the distribution samples which you are over here, which you are having here. So this means if you sample from this distribution, it will be a fake samples. It will be fake samples, obviously, because this distribution is not the same as this distribution. So whatever samples you take will be a fake samples. So now what will happen is this particular, we again have one more block. So we discussed that we had this block. Now we have one more block, which is this, which we are calling as discriminator. So this is basically called as discriminator. And this is basically a generator. So now we have two neural networks or two CNNs. So you can see the first network was here, which generates the samples. And there is another network which actually tries to judge, or it tries to discriminate whether this distribution is same as this distribution or not. So as you can see that this is basically trying to take the place of KL divergence or JSD divergence. This is trying to take that place. So in terms of modeling, in terms of neural network modeling, we are doing it, and we are replacing JS divergence or KS divergence by this neural network model, which compares this distribution, which is a D hat with D. So it is modeling that. So what is this discriminator model? This discriminative model we have already discussed. If you recall, this discriminative model is this one. This one. So this is like, what it will do is it will actually judge whether the images are real or it's fake. So right now it's cat and dog. We are removing it. We are saying whether it's coming from real data set or it's coming from fake data set. So it's also a discrimination that is trying to achieve over here. So basically this neural network is doing that. So what happens is we attach a label y equal to 1 with this data set. which is the original data set. And we attach a label of y equal to 0 with the fake data set, which is coming from the downside. So now you have a training sample where you have real data set and fake data set along with the labels. So now the task of discriminator is to discriminate between these two branches. This is a real one and this is the fake one. So if this discriminator is able to distinguish between the two, that is, if it is able to distinguish that okay, this sample from this distribution is real and this sample from this distribution is coming as fake, then what will happen is that means your D is not equal to D hat, because your model is able to able to judge that sample coming from real data set is different from the sample that is coming from D dash. So what happens? The discriminator creates a very high loss. It's a high loss. No, sorry, it will create a very low loss, because as far as the discriminator is concerned, it was able to judge the two. But there may be a situation where when you keep on iterating, like when you keep on iterating from here to here to here to here, like as you advance, what will happen is when you keep on iterating, it might be the case that your discriminator becomes poor in understanding that D dash is same as D or not. So it will fail to understand that D dash is same as D or not. At that time, what will happen? It will generate a maximum loss. So this is the point where it generates a maximum loss. This is the point where your D will exactly become equal to D dash, because your discriminator fails to distinguish the samples which are coming from D dash and from the samples which are actually coming from D. So we are always, in basic machine learning targets, in basic machine learning tasks, what we always try to achieve is the low loss. What we try to achieve is always a low loss. But in this particular task of generative adversarial network, what we are trying to achieve is a maximum of loss. We want this discriminator to create maximum loss so that our D dash becomes equal to D. That is what we are trying to achieve. So this maximum loss is our target. So what happens is the loss that it incurs, it's back propagated. The loss that is incurred by this discriminator is back propagated, and then it will adjust the weights of the discriminator and the generator. So when it adjusts the weights of discriminator and generator, with each iteration, your discriminator and generator will become better and better, and there will be a situation that at 1000 iterations your discriminator will have a very good boundary which looks as close as possible to this D. So in this situation where your D becomes somewhat close to D dash but it is not exact, the samples that you will take from this distribution will now be somewhat similar to the samples that you have in this distribution here, which is D. So this is what exactly the role of generative adversarial network is. So in generative adversarial network, we have two networks which are actually fighting with each other. We will see how they are fighting, like the adversarial concept, that is max min, which I was telling you. We will discuss that in our coming slides. If you have any questions here till now, you can ask me.
Sir, we have one question from Shripati,
Yes.
and the question is, what is necessity of taking noise image in Z?
Oh, so this is what he's asking, like why we are taking this Z, right?
Yeah.
So there is no, as such, if you are trying to generate the data, so here, see, what is generation? Generation is you are trying to come up with new data set, right? Every time you are, but there are some applications where there is no point in taking Z, you can feed in an image also, which is of not image, but it's a vector, which you can take to feed it into the generator to come up with a image. In case of super resolutions, you can do that. But for this particular task, it has been seen that if you take a random seed coming up from the normal distribution or from the Gaussian distribution, then it's good actually. So we are trying to come up with new images which are not existing in the data set. So these random seeds are not overlapping with the seeds that you have for the test images in the probability distribution. So it tries to provide you with a different seed from where you can generate different images which are not there in the data set. So that's why we are requiring this Z.
So we have one more question from
Yeah.
Swati Mathur. How
Yes.
we are calculating loss?
Yeah. So I'll come back to it. So this is just an explanation that I'm trying to say to tell you, but these mathematics will come in the next part. I will explain it. So this is basically again a picture which I had taken from internet. So this is also showing you that same concept, but in our earlier case which we were discussing, we had cats and cat images, and we were trying to generate uh, artificial cat image which is not there in the data set. But here this similar concept is can be replicated to MNIST data set also. As you can see over here, we have a real data set from where you are taking a real sample, and this is a noise from where you are actually creating a fake sample, and then you are using discriminator to discriminate between the real and the fake. This is just showing you that same thing, but with MNIST dataset, which is quite famous in the area of for testing. So it's a toy dataset which normally people use to for their research. So not for research, but for you know for a proof of concept. So if they want to do it, they start it with this dataset. Okay. So the learning mechanism that is coming up in this particular strategy is like what we are doing. We want to actually learn the discriminator as well as the generator. So the first step that is involved is training the discriminator. So what we do is we train the discriminator first, keeping the generator constant. So we will not touch it. We will actually train the discriminator. So in that case, what we do is we take a random noise vector, feed it into the generator, create an artificial instance of the MNIST dataset, and here you have the original instance which is here, and you can see the labels corresponding to the original one is y equal to 1. For artificial it is y equal to 0. So from here you can see that you have different instances, and then discriminator is basically trying to discriminate whether it's a fake or a real sample. So this is what you are doing during the training of the discriminator, and the important thing is you will train the weights and bias of the discriminator here, but the weights and bias of the generator will be fixed. You cannot train them. So this is first step in the learning mechanism of the generative adversarial network. The second step is, once that is done, you train the generator. In training the generator, what you do, you keep the weights and bias of the discriminator constant. You cannot change them. Once it is trained during the first process, you keep in the second step, you keep these constants, and now you train the weights and bias of the generator. So what you do is you take the random vector, you convert this into an artificial instance. But now important thing is what you do is you create an adversary. Basically, you are trying to fool the system by telling this discriminator, which is already, this discriminator has already learned that whether this is y equal to 0 and this is y equal to 1. But now you are actually fooling this discriminator by artificially, putting a label of y equal to 1 here, and you are saying, okay, this is the real image. You are actually trying to fool the discriminator by saying, okay, this image which I have generated is the real one. You tell me whether you can discriminate it or not. But again, now the problem is that this discriminator, if it makes a mistake in doing this, then what will happen is it will actually tune the if this particular thing fails to do it, then at that time generator is completely trained and proper, because generator is successful in creating the artificial image which discriminator was not able to detect. But if it passes, like if it can detect, okay, this one is a not the this is not the real image, it's a fake image, then you have to again train the generator in a proper way, so that you can create the image in such a way that even if you put a label of y equal to 1 on that, discriminator fails to identify it. So this is basically the training of discriminator as well as the generator, which we do step by step. Like you first train the discriminator, then you train the generator, then you go back, train the discriminator again, keeping generator constant, and then you come down, then you train the generator keeping the discriminator constant. So you keep on repeating this exercise for each of the epochs till the generative adversarial network is trained. So now, as one of the participants was asking about the loss function, so what we will do is we will actually we will derive this loss function, which you will normally find in the literature, from scratch, so that you will come to know, okay, this is the theory which is coming up, and this is the way this loss function is written in the research paper. Because you will see that in research paper they have directly written it, they have not derived it, and this is a research paper, we cannot expect them to do that. But as far as the fundamentals are concerned, it is coming from a very basic concept. So what I'm trying to show here is that, so before doing that loss function derivation, I just wanted to show you the terminology that we are using while deriving that, so that you will be comfortable with what we are writing over here there. So this is basically what we are doing is this particular thing which we were earlier writing as capital D, I'm writing it as P data X. This is the random variable capital X, which actually takes a sample small x from this distribution P data X. And then we have Pz of Z, which is the distribution from where we are taking the small random variable Z, which we are picking up from there. And this is the generator, which I am representing with by capital G. And we have these two dots. That means we are taking input as a vector. And then we have theta G. This theta G corresponds to the weights and bias of this generator, which will be adjusted during the back propagation. And similarly, this D represents the discriminator, where you have theta D, that is actually the parameters that are weights and bias of this discriminator, which are actually adjusted during the back propagation. So these are the weights and bias of discriminator. Now, this distribution which is coming over here is actually Pg of G of Z. This is basically the probability distribution generated by generator. So we are saying it as by Pg. And inside this, we have a variable which is G of Z, because Z is going into this transfer function and it is converted into G of Z, which is a fake sample. So now this sample, which is represented by G of Z, is fed into the discriminator, which actually these two dots are telling that you are taking input as an image. So the first dot will be X, which is going into this. So the discriminator will actually generate D of X, which we will say that it is operating on the real data set, which is X, and it will generate a probability value which is in between 0 and 1. In the second case, the artificial data which is generated will be actually written as dg of z, and this means discriminator is operated on the generated sample, which is g of z, and again it's a probability, so its value will come out to be between 0 and 1. And what is our target? Our target is that this Pg of z, which is this distribution, has to be close to P data of x. This is what we were trying to say from from the very initial start. So P data of x is this thing. So now these are the simple mathematical terminology which we will be using in our coming slides. So in order to derive the loss function of the generative adversarial network, we will start with the binary cross entropy, which I think most of you must be knowing it. So we are taking this concept from the machine learning point of view. So here you can see our loss is y log of y hat plus 1 minus log of 1 minus of hat. So this is a famous binary cross entropy function that I think most of you must be knowing. So now the important thing is the label for the data which is coming from P data of x. That is, from this distribution, whatever value of x that is coming out, it has a label of y equal to 1. This already everyone knows, right? Because this is the true data which we are saying. And whatever data that is coming from this generated sample, we are taking y equal to 0 for that. So this is y equal to 0 and this is y equal to 1. So now the label of the data coming from P data of x is y equal to 1. And you know that the estimate y hat due to the discriminator, when you feed real data into it, is represented by d of x, because real data is going, so your y hat will be d of x. So if you put these values of y hat and y into this equation, then what you get is this. If you just substitute these values, you will get this. Now, this is from the discriminator point of view. What I am discussing, this binary cross entropy, is from the discriminative point of view. Now, the second point is, if the data is coming from the generator, as I was discussing, we will have y is equal to 0, and the corresponding samples which we are taking, that is y hat, that is the generated one, will be d of g of z, as I discussed here, because g of z will fed into this d, and it will generate d of g of z. So this d of g of z will be the estimated value of the discriminator operated on g of z, which is the fake sample. So now we have his, this is the, once you substitute it in this equation, what you get is log of 1 minus d of g of z. So these are the two functions that we have obtained. First is this one, and the second one is this one. Now the important thing that comes up is for ideal discriminator. So if the discriminator is perfect, so what is the objective? Our objective is, from the discriminator point of view, what we want d of x has to be equal to 1. Why we want it as 1? Because you know that the samples which are coming from real data set are x. So if you operate discriminator on that, it has to detect it as real. So that is the main objective of discriminator. So this value has to be 1. Whereas, what is the second objective of discriminator? The second objective of discriminator is that if the fake data, which is g of z, is coming, then when it operates on this fake data, it should produce a value of 0. That is another important task that discriminator has to meet. So these two objectives, like d of x equal to 1 and d of g of z equal to 0, how to achieve this? Using these loss functions which we have derived. So what we do is, we add these two loss functions, and we write max of d over here. So what it means is, you are actually maximizing the argument which is here inside. You are maximizing this, and you are maximizing it with respect to d. Now you recall the example of cheetah and that deer thing that I was telling you. So one thing is coming up over here, that is a max which is coming over here. So now this max, now what we have to see is, if we are adding these two loss functions, which is this one and this one, so what we are saying is, how can this max function which is operated on this is trying to achieve this objective, which is this? That is what we are concerned about. Like, if I am putting, if I am summing, okay, no problem. But how come when I apply max onto this, will help us in achieving these objectives which are given over here? So let us see this. So if you see the log of d of x, if you plot this, it looks like this, which is on the left side. So this log of d of x looks like this. And the important thing is, d of x, as you recall, it's a probability and it has to be lying between 0 and 1. Then what you have to do is, you have to discard these values, because it's not in the permissible range. The d of x has to be in between 0 and 1. So we are discarding the rest of the part of the log which is beyond 1. So we have log of d of x here. Now the important thing is, we want to actually maximize this log function, because you are seeing we are doing a max, right? So when we do a max on this log, what it means is, you are actually going uphill, and this is the point where you have maximization, right? The value will be maximum at this point. So the value that is maximum at this point is, where it is occurring? It is occurring at d of x equal to 1. And this is what we wanted to achieve. If you recall, we wanted to achieve, d of x as 1 here, right? So we wanted to achieve this. We achieved it by putting a maximization on this log. And the second thing is, we have log of 1 minus d of g of z. So if you plot this curve, it looks like this, which is on the right side. And here again, if you want to do a maximization, you again go uphill. And what is the maximum value that you are getting? The maximum value you are getting at is this point. And what is this point? This point is d of g of z equal to 0. And this is what you wanted here. As I told you, like for the role of discriminator, you wanted both of them either to be 1 and 0 respectively. So that shows that if you maximize the terms which are over here, that means you are actually somewhere or the other achieving the objective of ideal discriminator, which is discriminating real samples as 1 and discriminating fake samples as 0. This is what you are achieving using max operation. Now, an important point that comes is from what happens with generator point of view. So from the generator point of view, what you want is that the generator samples that are generated by generator, if it passes through the discriminator should fail that, and it should produce 1 over here. So that is the objective of generator. That is, you produce a sample g of z in such a way, if you pass it through the discriminator, it should produce 1 and not 0. So the point where it produces 1 is the is the point where generator is successful in creating artificial samples. So now, how to achieve this target? This target, what we are saying is we can achieve it by using minimization operated on this loss function. So what we are doing now is we are actually neglecting this, and we are keeping only this, and then we are using minimization on g on this function. And why we are keeping only this? The reason why we are keeping only this and not this is obviously it's very simple. There is no g involved here. So since there is no g involved, so the only term which is having g is this one. So that's why we are writing minimization of g onto this particular one. Now the important thing is, again I will try to tell you that what is the you are trying to minimize this particular expression, and how come this minimization operated on this gives you this? It's very simple. If you see here, what is the minimum of this curve? The minimum of this curve is somewhere, it lies at infinity, but we are not saying that. We are saying let us be realistic and practical. So we will have some values close to 1, which is 0.9 or something like that. So at that point you have some minima, and you know that this is occurring at d of g of z equal to roughly close to 1. So that's why we are operating minimum of g onto log of 1 minus d of g of z. So now the complete loss function of the generative adversarial network is written like this. You have a max operated on this, and you have a min operated on this. So recall the cheetah versus deer example. We had min max over there, as if you can recall. So similarly here you have a generator and discriminator fighting with each other. So here you have this coming up in the generative adversarial network. And now if you see, this is actually what I have done is very simplified explanation for generate for the loss function, but in the book it's not like that. Oh sorry, in the paper it's not like that. So what happens is, this is for a particular example which I was telling, a specific x or random variable small x which I had taken from the distribution p data of x. So if you want to write the total objective function, it looks like this. Not be here. It should look it looks like this. So here you can see what we have is we have we have x sampled from p data of x, and then we have log of d of x, and then we have z which we are sampling from p z of z, and then we have log of 1 minus d of z of z. The expectation is coming because we are taking large number of samples and we are averaging the result. So that's why this expectation is coming. Right now, in earlier case, it was not, because I was taking only one example to explain you the theory. So as the samples are large, right, we have 60,000 images in MNIST data set, and for other data sets also there are tons of images. So expectation is coming because you are trying to average out the loss, and you are taking a large number of data set. So that's why this is the one. So this is the objective function or the loss function that you see in case of research papers for the generative adversarial network. So this is basically showing you, which I have taken from one IEEE transaction paper. I forgot to cite this, and even I think for me it's difficult to recall from where I had taken this, but this is one of the research papers which is not research, it's a literature review on generative adversarial networks from where this algorithm is taken. So here you can see what we are doing is we are sampling a mini batch noise sample from a noise prior PG of Z. And then we are also sampling a mini batch of M examples which are taken from a real data set P data of X. And then we are updating the parameters of the discriminator by ascending the stochastic gradient descent. And this is the loss function that we have already discussed. And this summation is coming because of the expectation operator. So it's a Monte Carlo estimate of the expectation operator. So we are just taking average. We are summing up till the M samples and dividing by the total number of samples. So here the important thing is you are ascending the stochastic gradient descent for training the generator. And why we are doing for training the discriminator? Why we are ascending? Because we are actually doing a maximization with respect to D. So we are trying to maximize the loss. So if you recall, our main target was to maximize the loss so that our discriminator should make mistake in discriminating the real and the loss, real and the fake data set. So since we are doing a maximization, so that can be done only by ascending the hill, because if you want to maximize a cost function, you have to ascend the hill, and that is done through stochastic gradient descent. So that's why we have ascending over here. And once we train the discriminator here, and please note in this particular situation our generator is constant, we are not training the generator. Now once that is done, we again sample the M noise samples from the random prior PG of Z, and then we train the generator by descending the stochastic gradient using this. In this we are descending because we are doing a minimization with respect to G, so we have to descend it. So now in this particular training task, our discriminator is constant. We are not training the weights and bias of the discriminator in this situation. So this is basically a general, algorithm for doing your generative adversarial networks. So the loss function which I have discussed just 2 slides back is repeated again here on this slide. So what interpretations we can get from here is important. So let us see the interpretations. So the interpretations are that what is the best discriminator that we can have in real sense. So what I'm trying to say is like what is the benchmark of saying that this discriminator is the best, like in terms of providing a high loss, like in terms of detecting whether the data coming from the real and the fake, it's not able to do it. That is the best data, best point where we can say our discriminator is the optimal one. So that optimal discriminator which we are representing at by DG star, the star if you can see over here is the optimal one, that is obtained by this expression which is P data of X upon P data X PGX. So our objective is that our P data of X has to be equal to PG of X. As you all know, we want our generated probability distribution is to be same as the original probability distribution. That is our objective. So if you substitute this value, then this value comes out to be 0.5. So that means when our discriminator gives a value of 0.5, that means at that point it fails to distinguish whether the data coming from real is real or coming from fake is real. So it fails to do that, and that happens when your discriminator value comes out to be 0.5. So that is the optimal discriminator that we can have from this setting. So this is actually one of the propositions which was given in paper. So I have just taken it from there. And the important thing is how to derive this expression, which is not discussed in details over there. But I'll try to glance through it in a very high way, in a speedy way, so that but details you can see in my lectures which are there. I will show you that links also. But for now, I'll just quickly go through the glancing of these equations, so that you'll get to know what exactly I'm trying to say. So what I'm trying to do here is like I wanted to prove this particular thing which is over here. I want to see like whether this particular DG star is actually this expression or not. So what we are trying to do is we are trying to actually get the optimal value of DG star, and that we can do it by argmax on the loss function. So this is VD of G is nothing but a loss function which we have just discussed. So we are trying to argmax on that. You know that because we have already written that with respect to discriminator, we are actually maximizing the loss. So you know that the expectations can be written like this in continuous form. This, I think, from the probability distribution, you can get to know this. And now the important thing is we are trying to apply this expectation over this particular expression. So what we get is this. This is what we obtain. An important point here is, the expectation onto the second part is with the probability distribution Pz of z. And then we have log of 1 minus d of g of z. Here we have p data of x, and then we have log of d of x. So the important point that I want to discuss is, like, you cannot add these two integrals, because as simple as that, because the distributions which you have on the left and the right, like p data of x and pg of z, they are different, so you cannot club them together. But actually what happens is, in the paper, what they have done is they have actually somewhere or the other written this as this. Like, what they have done is they have written pg of z as pg of x. So it was very confusing, like why this particular integral, this probability distribution is replaced by the generator distribution, and there was some transformations here also. So it took me some time to get to figure it out. So I'll just give you a quick glance onto the proof why this pg of z is replaced by this and this g of z is replaced by x, so that you can get to know what exactly is this. So our main target is to actually make this particular thing which is on the left side to be equal to the right. So how we can do that? If you recall the concept of probability distribution, so basically it's coming from probability density function. So basically what happens is, if you have a random variable x which has a PDF which is given by this, so it is possible actually to calculate the PDF of some variable capital Y, which is actually a transformation of the random variable x through this capital G. So if you have a transformation which is already happening, G is operated on X and you are getting a random variable Y. So because of the using the change of variable concept in PDF or in probability, what you can do is you can actually define the probability distribution of Y as this. So you can get this probability distribution of Y if you know the probability distribution of X using this expression. So now this is actually represented in block diagram like this. So what happens is, you have X, you have its corresponding PDF, and there is you know the transformation which is Y equal to G of X. So what you want to know is the P of Y of Y. So this is obtained through this expression. So in our case, if you recall, we have our generator G, which actually takes random seed Z from PG of Z, and it generates X prime, X dash I am writing because somewhere or the other they are similar to X, which are the real data set, so I'm writing it as X dash for simplicity, and they are G of Z because you are transforming the Z from the generator to get you value this. And now if you substitute X as Z and Y as X prime, then what you will get is you will get this expression which is given over here. As simple as that. You have to just substitute these values here to get these values over here. This is very simple. And just for transformation of the variables, it will not hurt us. So what we are doing is we are replacing x prime by x. So it was like this. So this is the expression that we are getting for Pg of x. So let us see how we can use this to get the equivalence of left, which is given over here, to the equivalence of the right, which is given over here. So if you recall, I just repeated the proof again here, which we want to show. So what we are doing is, we are writing Z is as G inverse of X, because this is from here. So we are assuming that this G network which we are having is an invertible network. So we are assuming that it's a strong assumption. And for that, what we are getting is Z is G inverse of X. So if you start from the left-hand side of this proof, if you start from the left-hand side, which is given over here, what I'm doing is I'm actually replacing Pg of Z by, I'm replacing Z by this G inverse of X. So if you can see, Z is replaced by G inverse of X, and here G of Z is replaced by X. So it's here like this. And again, here Z is replaced by dG of inverse, like this. So it's just a replacement of the values. I'm putting Z as this in these equation to get this. Now what I'm doing, I'm actually dividing by dx on both the sides like this. Just a slide manipulation. So once you have this, You already know this derivation which we have just derived. We can put this appropriately here in this expression. We can put this. So what we are getting is Pz of G inverse, and then we have log 1 minus dog of inverse. Then we have, so this is just, I have rewritten again. This equation I have rewritten, this one. So it's rewritten again. And then I am recollecting the terms. And the recollection of the terms are these two. So which is this term and this term are recollected and is represented and clubbed it together here. And then we have log of 1 minus d of x. And then we know that this particular thing which is given over here is actually a combination of these two. So it's Pg of x here. So we can say that now what we were trying to prove, that this is equivalent to this, is done. So now we can rewrite these expressions which we had written earlier into this expression, which is given over here. So now what happens is, what we are trying to do now is we are trying to find the optimal D. So now the optimal D star can be obtained by maximizing, as you already know. So this one we are trying to maximize. So what we do is we take the derivative and see the maximum point where we can get the value. So once you take the derivative of this expression, you will get to know that this optimal value comes out to be this. You can check back later, but this is the one which we are trying to find out. So in order to prove that this is the maximum, we again take the double derivative and see that it's negative. So then we are double sure that the optimal value that you are getting is this. So this is just the proof of the paper which was written by Ian Goodfellow. So this is just a derivation for that, to give you more insights of what's going on in that. Similarly, if you want to calculate the optimal generator, as it was in the case of discriminator, we had optimal D. Same, you want to know the optimal G also. That can be done by minimizing the loss function, which we were already writing. So this is actually a loss function. And the important point is, in that loss function, we are putting the optimal discriminator value, which we have calculated here. So we want to put this value into the loss function so that we want to find out the optimal generator. That is our target. So that can be done by substituting the value of dg star, which we have already calculated, into the loss function. So let us do that. So this is basically the equation that we had already written in our earlier slide. And now we are actually minimizing it with respect to G. This is the minimization with respect to G, which is happening. So now whatever is highlighted in yellow is basically the optimal DG star that we want to substitute here, because we have already calculated and we want to know the optimal G star now. Now what you do, you substitute the value of DG star here, which we have calculated. For this, you calculate this. And then we do a slight trick. We actually add log of 2p data of x and add and subtract these two terms in the above equation. The one which we have written over here, we add and subtract this term, and we add and subtract this term. So if you do that, you can see whatever is added and subtracted is written in different colors. So you can immediately realize like what is the additional thing that we have added here, and it's not changing the complete expression also, because somewhere or the other you are adding and subtracting the terms. So this is the first term which we have done. This is the second one. And similarly, what happens now is, now we are, after this, we are actually rearranging the terms, and we are taking minus log 2 like this, and we are adding p data of x, pg, x, ds. This is just rearrangements of the terms. And then we are pushing in log 2 p data of x like this. So this has a specific reason for doing it, but this is what the readjustment of the terms we are trying to make in the original expression. Okay, so now if you rearrange this term again, then what you will get is something like this. This is the, after some readjustments, you will get this value. Now, once you have this, let us move further. After this, what you will realize is that this thing actually turns out to be 1 plus 1. Why it is 1 plus 1? Because you are actually integrating the whole PDF of PG of x and P data of x. So you know that if you take the complete integration of the density function, these values will come out to be 1. This will also be 1. So it will add up to be 2. So now that's why it is minus 2 log 2. So it's basically minus 2 log 2 or minus, sorry. So this is minus 2 log 2. This is the one which you are getting. So it's minus log 4. So this is basically the first one. And in the second, what we are doing is we are actually dividing this log 2 into this, and we are actually dividing the log 2 into this, and what we are getting is something like this. So this is just readjustments. So we are putting 2 in down like this. Both the expressions are same. So now if you again solve, so what you get is minus log 4 as I told you. And then we have an interesting concept which is coming out here. That is this particular term, this particular term which you have here is actually a KL divergence, which is, this as a whole is basically which we call as a KL divergence, which we started off with. So KL divergence basically tries to find the distribution similarity, like how close the two distributions are. So somewhere or the other, you can see here now that KL divergence can be this particular expression can be written in a compact form as this. That is KL P data of x, and this is the representation of definition of KL divergence. So this is the one. So if you want to recall from Wikipedia, you can see the KL divergence of the two PDFs which are P and Q here. These are the two distributions. If you want to calculate the KL divergence between the two, it's basically written as this. So this is basically the KL divergence between the two distributions which are written over here. Similarly, you can write the KL divergence for the second term which is given over here. So that also can be written like this. This is the KL divergence for the second term. And now what we can do is we can combine these two terms together. And that can be done by using Janssen-Shannon divergence, which actually takes these two terms together and combine them to form one single expression. And if you want to see what that is, you can see the expression for Janssen-Shannon divergence in terms of the KL divergence of the two DPDFs, which is P and Q, and there is an intermediate PDF which is M and M here. So this M is nothing but it's P plus Q by 2. So it's an average. So basically you can actually represent these two terms which are represented in two different expressions into one compact expression as JS divergence. 2 times that. And this 2 is coming because you have 1 by 2 here. Now the important concept that comes is you want to minimize this expression, right? So you want to minimize this one which we had already started out from the top, because this is somewhere or the other loss function which we were trying to minimize. So this minimization, the minimum value comes out to be minus log 4, because this term has to be 0 in order to minimize this particular expression, and the minimum value is minus log 4. So if you want to make this term go to 0, which happens when you operate argmin on this, so this argmin on G will force actually JS divergence to become 0. And when JS divergence becomes 0, it becomes 0 only when PG of x is equal to P data of x. This is our objective, the prime objective. That is, we wanted our generator value, the generated samples, to be close to the actual samples. So that happens alternating as when your JSD is becoming equal to 0. That is the main thing. So that is the importance of doing a minimization on the loss function, because somewhere or the other its JSD becomes equal to 0 and the probability distribution matches each other. So this actually yeah, so another important thing, so this is just another derivation trying to show you same proof but in different format, this theorem. This is not, I'm not going into the details of this one. And other important concept that I want to tell you is that during the training of the discriminator, as I told you, that with respect to the minimization of the G, what they have proposed was to use log 1 minus d of G of x, which I was telling you earlier, which we had defined also. But now what they have realized, that during the practical implementation of this generative adversarial network, what important thing that comes out to be, what they realized is, instead of using this, it was good that if they use this. So this was actually a modification that they have done, because somewhere or the other this particular thing was not a right choice. So what they did, what they found out was to replace this particular thing by this particular thing. And why they went like this is because if you recall this particular, expression, which is 1 minus d of g of x, you recall it's like this, as I was telling you earlier also. And what is the ideal settings of generator? The ideal settings of generator is that d of g of x has to be whatever. So the problem is during the initial iterations. During the initial iterations, what happens is our discriminator is very smart actually. Discriminator is trained properly, because if you recall, we trained the discriminator first and we kept the generator as such. So at that type of, and in that situation, what happened was our discriminator was very smart. So what happens is whenever you feed a generated sample g of z into this discriminator, our discriminator will immediately reject it and it will say, oh, this is correct, this is actually a fake, let us put it as 0. So if that happens, there will be very less learning that is happening for generator, because whenever generator tries to you know come up with a sample, discriminator immediately rejects it, because it's a very smart discriminator at right now. And one of the reasons for this is that this particular loss function that we are trying to incorporate, if you see what is happening right now, is d of g of z is actually 0 in this initial iteration setting. So in this, what happens is we are actually operating at this point. And if you recall, because we are doing back propagation, somewhere or the other gradients are involved. So if you take the derivative of this particular curve, then what will happen is this derivative will be, this derivative will be, like this. And it's very, very less, small derivative. But if you try to use this function, then you will see that this function looks like this. And in this initial stage, which is d of g of z, you are actually operating at this point. And at this point, you can see the slope of the derivative, which is actually responsible for gradient descent. You can see now, like for this particular slope, this slope is very high compared to this slope. So these gradients will actually help us in learning, in the learning of the generator during the initial stages of the training, which was very hard if you were using this particular loss function. So if you see the paper, then you will see at the end of the paper when they are discussing, they say like, let us replace this by this. So this is the reason why they are doing it. So these are some of the samples, snapshots which I had taken from web page. So you can see like in the initial starts of epochs, you can see the MNIST data set was generating these images, which are not that good, because you can see in the initial starts, like first epoch only, you are putting the dots, and these dots are random dots, which are not exactly the MNIST data set. And then as you increase the epochs and you are going from 1 to 100, as you keep on increasing, you can see the quality of the MNIST images are getting improved and improved every time. So you can see from epoch 1 to epoch 100, you can see, the text images are this. And now after 200 epochs, it's becoming better. And if you keep on going and if you keep on going, then the quality of the images will become much better and better. So this is basically, a general, viewpoint on how this particular, generative adversarial network generates these samples. So this is just giving you some of these images that are doing that. So if you have any questions related to this particular, discussion which we had done, you can ask me.
Sir, we have one query from Mr.
Yes,
Shripati.
yes,
What
please.
can we say if optimal D lies between 0.5 and 1?
See, the thing is, as far as the optimal D is concerned, from the settings, from the derivation point of view, if you see, that happens when only your PG is equal to P data X, then only you will get 0.5, right? But if you are going above that, then definitely that equality is not valid, because somewhere or the other, you are the densities are not matching actually. So there is a difference in the densities. So So these densities which we are discussing, like for example, in the two-dimensional version, we are saying that these two densities, which are p data of x and pg of x, they are not close to each other. So there is some dissimilarity here, and your particularly your what you say, your discriminator is smart enough, and still it can detect the differences. So that's why that is not a good point to achieve. So what we are trying to do is we are trying to maximize the loss. We want our discriminator to get fooled. So that can only happen when these two distributions actually become close to each other and sit overlap, and that happens only when the value comes out to be 0.5. That is an optimal setting.
Thank you, sir. Do we have any other query from participants? Please mention your query in the chat box.
Okay, so I suppose there are
Okay.
no queries, huh?
Yeah,
So,
thank you.
so what I'll just do is I will finish off this discussion with showing you some of the problems that we have in GANs, and then we can finish off this topic. So the first problem that you encounter while training the GAN is what we call as mode collapse. And in mode collapse, what happens is as you keep on increasing the epochs, what happens is at some stage there will be a case that you will have similar type of images coming up like this. If you recall, if you generate the images, you will find out that somewhere or the other similar type of images will come out. And this happens because because we have and researches are actually going on in avoiding these mode collapses. So maybe you can find out in the latest research paper, people must have definitely solved it. I have not gone through this in particular, but whosoever is interested in doing research in this area maybe can look into this particular topic of mode collapse and can look into how to avoid this situation. But normally what happens is any any image data set which is very very high dimensional, so it happens that sometimes there are multimodal distributions where they sit actually. So for example, if you have MNIST data set, in MNIST data set we have 0 to 9 images, and uh, each of these images will have different orientations and different bends. Like for example, if this 0 can be represented as this, in this way, or in this way, something like this. So this will actually form one distribution of zeros here. Then you have a distribution of nines also, which is like this or this or this. So it can form another distribution like this. So we have a multimodal distribution or a complex distribution which having multiple valleys for any real data set. So what happens is this particular GAN gets stuck into some valley like this. So it gets stuck in this valley. And what happens is the main job of generator is to fool the discriminator. So obviously, by stucking in this valley, that is like for valley for zeros, if it is stuck in this valley, it can keep on generating these data set only, because the objective of the GAN is to fool, objective of the generator is to fool the discriminator. So it can easily do it by stucking in this valley and create a different type of zeros. And there is no way they want to and there is no way it will go into this valley where you have you know samples of nines, or maybe other way also it will stuck in here and generate multiple nines. So this type of problem happens, like you have simple same images coming again and again because it is stuck in one of the valleys of the multimodal distribution. So people have come up, and maybe you can look into the research papers on this, how to do this. So some of the PhD candidates who are, if they are sitting, can look into this type of problem also. So this is the first thing that I wanted to discuss. And the second is, sometimes the images that are generated by the discriminator, there are some problems in terms of the counting. So it's not able to, really identify that, if there is an animal, then it should not have, multiple eyes or multiple heads. So it's difficult for GAN to understand that. So somewhere or the other, understanding or feeling of the data, somewhere or the other is missing at the higher level. So that's why you can see images which has multiple heads and eyes are generated by this GAN. And then we have problems with perspective. Sometimes it's difficult for the GANs to generate 3D data, because nowadays, as far as research is concerned, I think some of the advancements that are made, maybe they are successful in doing that, but some way or the other, when I prepared these slides at that time, it was difficult for GAN to generate 3D perspectives. So it tries to, it cannot identify the 3D projections, and it once it projects it onto the 2D image, it creates these type of artifacts. As you can see, the images of the animals, they do not look exactly as animals, because somewhere or the other, the 3D projections of the background are, somewhere or the other blended onto the images of the animals. So this is a problem with the perspective that we have for GANs. And then, as far as I was telling you, it is difficult to, for the GANs to understand the global structure. So sometimes, it will create 5 legs and, 2 heads for these animals. So you can see here, for this particular thing, it has created 5 legs and, somewhere there are multiple heads, and these type of images are not perfect images for the animals. So these are the some of the research problems which you can look for to improve upon, like if you can do that. So this is my take on generative adversarial networks, and thank you so much for attending this particular session. So in case if you have any questions, do let me know so that I can answer them.
Thank you, sir. We have one more query from Dr. Pranati Rakshit.
Yes, please.
Some application area of GAN model where this model can be used.
For application area of GAN models.
Yes, sir.
So you want to know the application areas, like exactly, I was
Yeah.
not able to
Yes.
follow.
Yes.
Yes. So, okay.
She's
So
writing yes.
basically, there are tons of applications that you can find out for GAN models. Like for example, if you want to generate artificial music, so what happens is, like, if or maybe artificial lyrics, like this can be also done through generative adversarial networks, because generative adversarial networks, what is the main objective is to learn the distribution and then create artificial data for that. So 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 basically, you can generate artificial samples also for any ECG signal. So somewhere or the other, it can help you in data augmentation also. Like, for example, if you are, if for example, if for my current research, if I want to share you a few points of that, what happened was, we were trying to, come up. We collected actually some of the data from the sensor, and that sensor data was not that enough. So the data of the sensor was not that enough, and we wanted to retain the spectral and spatial relationships of that samples, that the signal that we were obtaining from the sensor, and the data sample that we got from the sensor was not that enough. So we used GANs for generating the artificial data samples, which actually generated really very good samples, which were very close to the original sensor data, which which was possible if we are not using GANs. So somewhere or the other, you can use augmentation of the data by creating artificial samples. There are tons of applications for this GAN. Somewhere or the other, you can do, you can convert the images from winter season to summer season, or you can convert the images of satellite images into maps, like Google Maps. Or you can do the reverse also, like from maps you can come back to the satellite images. So there are tons of applications. There is no limit to imagination. Nowadays, GANs are used for mostly a wide variety of applications. So you can work around and see different type of applications, and whatever suits you, you can use that. So for super resolution also, you we can use generative adversarial networks for super resolving the images. For image denoising also it is used. For image dehazing also it is used. So there is no limit to it. Wherever you find it, it will be there.
Thank you, sir. We have one more query from Mr. Ajit Singh. His question is, can we use GAN model to detect the fraud cases in banking domain?
Can be done once you, but the problem is, you have to understand the probability distribution of that fraud cases. Like you have to provide the data set so that somewhere or the other generative adversarial network should learn the distribution of the typical kind of fraud cases. Like if that distribution is learned, definitely you can use it for doing that. So the important thing is distribution has to be learned, and you have to see how you can make that possible, like for this.
Thank you, sir. Any other query from audience? Okay, thank you.
Okay. Okay, then thank you so much. So can I leave now?
Yeah, thank you, Dr.
Okay.
Kumar, for
Thank you
such
so
an
much.
informative session. We
Thank
are
you.
certain that our participants learned a lot from this session. Thank you so much,
Thank
sir.
you. Thank you.
In the next session, Professor Nidhi Goyal, Head of Electronics and Communication Engineering Department, Indira Gandhi Delhi Technical University of Women, will be addressing you all. She will be briefing you about Indira Gandhi Delhi Technical University campus and organizing committee of this faculty development program. And the next session will start at 2:30 p.m. So, okay, thank you.
Good afternoon, everyone. On behalf of Indira Gandhi Delhi Technical University for Women, I feel privileged to extend my warm welcome to all present here. Today's talk on data science and artificial intelligence will be presented by Professor Nidhi Goyal. Professor Nidhi Goyal is the head of the Department of Electronics and Communication Engineering at Indira Gandhi Delhi Technical University, New Delhi. Before joining IGDTUW, she was associated with Delhi Technological University. She has teaching and research experience of approximately 20 years. She received her BE degree in electronics and communication and MTech degree in digital communication in 2001 and 2006 respectively. She pursued her research interest and completed her PhD from IIT Roorkee. Her areas of interest include medical image processing, deep learning, artificial intelligence applications, multimedia security, computer vision, and soft computing techniques. She has published 4 book chapters and over 65 research papers in reputed international journals and international conferences. Over to you, Nidhi ma'am.
Thank you, Achita. Thanks a lot. Give me a couple of moments. I'll have to configure. I just wanted to, actually check my audio and video, whether it's coming or not. Give me a couple of moments and we'll start. By that time, I think participants will also increase. It's 81 right now. So let us wait for 2-3 minutes.
Sure, ma'am.
Achita, you need to tell me whether the video is visible and the audio is coming perfect.
Ma'am, the video is visible.
And what about the audio of the video?
Ma'am, can you play it once?
Yeah, sure.
No, we can't hear the audio.
Okay. Um, Shall I share the video with you? Maybe you will be able to, play it.
Yes, ma'am, I'll try.
Okay, I can do a different. Please check the audio and let me know. Archita, was the audio, could you hear the audio?
Ma'am, I couldn't hear the audio.
Hello. Hello.
Hello.
Sorry, I think I wasn't able to hear anything. Could you hear the audio then?
No, ma'am.
I'll share once again, the last try. Was it audible then?
No, ma'am, it is not audible.
I'm surprised how. Uh, okay, the last try. Now,
Ma'am, please press the play button.
no, the video won't play. The video won't play. But could you hear the audio?
No.
Now,
No, ma'am.
No, ma'am.
no. Okay. Uh, what I'll do, Archita, I'll just share the link for this video. Please try it from your end once in case we are able to do that. I have shared it on the WhatsApp.
Okay, ma'am.
Every day we escape losing our.
Yes, Archita, it was audible as well as visible.
Okay, ma'am. Then I'll share it.
Yeah, you can share it. I think now we can start. You have already introduced me, so I'll just start.
Okay, ma'am. Shall I play the video now?
No, when I say.
Okay, ma'am.
Yeah. Very good afternoon to one and all present over here. I could see 90 participants and the students, it's my team which is working at the back end. And let me start my video. Yeah, good morning one and all present over here. Before I start with the session, let me introduce myself. The students have already done that, but let me introduce myself as I am the coordinator of this particular FDP, and we had actually scheduled the inaugural in the morning before the ATAL inaugural could take place at 11. So we were thinking of having an inaugural in the morning from 10 to 11. But coincidentally, we had some important meeting which came urgently, and that too was with external members. So we had to postpone that particular session. So we have started, I thought of just squeezing in 10 minutes from, this particular technical session so that I can introduce my institute, because I can understand there are many participants who have been from various parts of the country and joining, and it's definitely a very good platform given by ATAL AICT Academy, so that, it has broken all the barriers, and people from across India, even from the southern part of India, they can join for a FDP in the northern part of India. So that's great, which was not possible in the physical mode as such. Before I start with the session, I'll take just 5 minutes. I am representing, or you can say that I'm working at Indira Gandhi Delhi Technical University for Women. It's a small government institute in Delhi, and we are going to make it big very soon. We have been working very hard in the past, and it's a purely women's university. And we offer courses from BTech, MTech, we have MCA, MBA is there, PhD programs are offered. And we have been doing good in the research and the rankings part. We have been in the WURI rankings. Recently, we have been given a 7th position in the Times higher rankings, so on and so forth. So you can go to the university website to have a detailed look. Before I start, since it's a technical university, I'll just play it. I think it's a 2-minute clipping, not more than that. That will give you an idea of the university in short, because I can go on saying or praising the university like anything, but I I guess all of you will believe your eyes rather than listening to a half an hour lecture on the university's praises. So the video that we are going to play is from INNER, which is the Technical Festival of IGDTUW, and wherein this technical festival is organized by the students and for the students. They do everything right from the start till the end of the program, getting up sponsorships, managing the events, proposing everything. The video that we are playing is of 2019. 2020 also we had in the online mode, but since all of us are aware that in online mode we can have just the screenshots. So we want to give you an actual glimpse of the festival. So now I request Archita to please share that video, play that video.
Ma'am.
Every day we escape, losing all of our faith. We can't live this way. Feel me slowly fade away. All the words I could say just can't really seem to stay. Feel me slowly fade away.
Yeah, thank you, Achita. Thank you. That was just a small brief of IGT2 and inner about the technical fest. Now we'll start with the technical session for this particular session. I'll just share my screen. And I'll just stop my video as well so that there's no problem for the bandwidth. I hope my screen is visible.